In the last session, I introduced you the concept of group velocity, which is the speed of energy propagation for an electromagnetic wave. And when I introduce the group velocity, I show you a wave packet propagating in space. And to form the wave packet, you have to add frequency components into the electromagnetic wave, and then slowly the energy will bunch into some small portion in space. And turn out that for different frequency components, the speed of the propagation could be different. And this phenomenon is called dispersion. And this is the topic we want to talk about in this session. And naturally, you ask, how do we relate the group velocity to phase velocity? Well, we could just bring out the definition of the group velocity and phase velocity and do some algebra. And then you can come up with this expression. UG here is the group velocity of the wave. It's going to be equal to the phase velocity of the wave divided by 1 minus omega over UP dup over d omega, where this UP is the phase velocity. Apparently, if you take out this term, dup over d omega, then you will have group velocity equal to phase velocity. And in other words, if this dup over d omega is not equal to 0, then in general, the group velocity is going to be different from the phase velocity. When dup over d omega not equal to 0, this means that the different frequency components inside this wave packet will be moving at different speeds. And for example, think about this wave packet consisting of a few frequency components. And then it propagates over time. And during this propagation, the phase velocity for different frequency component will propagate at different speed. So in the end of this propagation, the different frequencies component will be separated in space. For example, in this case, I use the red color to represent the low frequency component and blue color to represent the high frequency component. And in this illustration, the low frequency component propagate faster than the high frequency component. And for this kind of pulse, we call this chirp pulse because there's a frequency chirp in this output pulse. And this phenomenon is called dispersion. Let's start the analysis on dispersion based on this expression. The first case is that when dup over d omega is equal to 0, this means that during propagation, all the frequency components will propagate at the same speed. And in this case, we say there's no dispersion for this case, and the group velocity is equal to the phase velocity. But if this dup over d omega is not equal to 0, for instance, is less than 0, this means that when you increase this frequency, this phase velocity will decrease. So this means that the high frequency component in this wave packet will move slower. And turn out that if you send a wave packet like this into some material or device with normal dispersion where dup over d omega is less than 0, you're going to detect such a stretch pulse at the output where you see that the high frequency component fall behind and the low frequency component will come out first. And there's one application for such a phenomenon. For example, if you prepare such a so-called upchirp pulse, high frequency component fall behind and low frequency component at the beginning, and then propagate back to the, this material or this device, then you will get this compressed pulse. And this process is called pulse compression. On the other hand, if you have dup over d omega larger than 0, then this means that your group velocity is going to be larger than the phase velocity. But when you increase the frequency here, then your DUP, this phase velocity, will also increase. So this means that in this system, the high frequency component will move faster. And so let's come back to this scenario. If you send a pulse into some material or device with the so-called anomalous dispersion, then you will detect a stretch pulse like this. The pulse length is going to increase, but in this case, the high frequency component will come out first because this high frequency component will propagate faster, and the low frequency component will fall behind. And again, if you could prepare such a down-choke pulse and then propagate this pulse back to this material or device, then you can also do pulse compression. And I want to use this slide to tell you the origin of dispersion. Think about you send an electromagnetic wave into some material, and the electric field will interact with the dipole. The field will pull the charge and cause the oscillation of the dipole. Apparently, there's a resonant frequency associated with this spring model. And if you excite it with different frequency, then this dipole will oscillate differently. In particular, if you set the frequency of the wave to be close to the oscillation frequency, the resonant frequency of this dipole. So when you send a wave into a material, the phase velocity is going to be a function of frequency, and there will be dispersion associated with the material, and we call this material dispersion. On the other hand, if you have some structure like a rectangular waveguide or a cylindrical waveguide, and in the next session, I'm going to show you that the propagation is going to be related to the structure. This H parameter is related to the structure of the waveguide. And turn out that omega and beta are not linearly related. So you have the phase velocity and also group velocity, which are functions of the frequency. And we call this waveguide or structure dispersion. 所以呢，在这一节我介绍了什么是 dispersion。dispersion 的话，就是这个波在一个结构或者一个物质里头传输的时候，不同的frequency component 会跑不同的速度。那在一个物质里头如果说这个物质是叫做 normal dispersion 的话，那代表说低频的这个 frequency component 会跑得比较快。但是 on the other hand， 如果说你是在一个叫做 anomalous dispersion 的 material 里头跑的话，那这个高频的部分就会跑得比较快。那这个 dispersion 呢，是来自这个譬如说物质里头的 dipole response 是跟频率有关系，跟电磁波的频率有关系，或者是呢，在一个结构里头，它这个波的传输也跟这个电磁波的频率有关系。所以这个小节主要是介绍这个有关 dispersion 的这些概念。